Hi, and welcome to this lab session at the Qiskit Global Summer School. In this lab session, I'm gonna show you how to implement in Qiskit some of the ideas and concepts that I introduced you in my previous class. So let me start this session by sharing my Jupyter notebook, which we're gonna use to work out the details of the Qiskit implementation. Okay, so the focus of this class is to teach you how to get a qubit Hamiltonian that models a certain molecular problems. And then we're also going to play with variational form, variational wave functions, and reference states that are both very useful to perform variational quantum algorithms. So let's get started. So the first thing to do in order to make a step forward to get a qubit Hamiltonian that represents our molecular problem is to get the 1 and 2 body integrals for a given configuration or given molecular configuration. So actually we outsource the computation of these integrals to other software, to external software. So the first line of this lab session is going to be to import from Qiskit a PyYSCF driver which we're going to use to compute the 1 and 2 body molecular integrals, and then also import a units type, which is going to set the unit for with which we're going to measure the distance, our intermolecular distances. So a molecule is a collection of atoms which is very energetically stable, and it is specified by the atoms that compose them and their position in a three-dimensional Cartesian reference frame. So to specify our molecule, let's give molecular coordinates. The molecular coordinates are given in terms of a bit string that describes what atoms are in the molecule. So in this case, since it's a lithium hydride molecule, we're going to have a lithium atom and a hydrogen atom. So we're going to place the lithium atom at the origin of our three-dimensional Cartesian reference frame, and then the hydrogen atom on the x-axis with respect to the lithium atom at the distance of 0.6. Now, to send the information to the driver in which unit it has to compute this distance, we're gonna set distance unit to angstrom. And also finally, a last ingredient to define our molecule is the basis set, which we use to compute these 1 and 2 body integrals. So since this is a small toy model problem, we're going to use a STO3G basis set. So the basis is going to be set to STO3G. Okay, now that we have set up the coordinates and the basis and the units of distance, interatomic distance for this molecule, we can actually run the driver that is gonna compute, which is gonna compute for us the 1 and 2 body integrals. So we're gonna feed to the driver the molecular coordinates that we have established before and our unit distance. Finally, we get a molecule object just by running that driver. And to check that everything is correct, we're going to print out on screen the matrix for the one-body integrals. So we get this matrix from the molecule as a field of the molecule object. And finally, we print it. There's a typo here. Okay, now that finally we got the one-body matrix for our lithium hydride molecule, we can also check the two-body integrals as well. Again, note that the two-body integrals are actually represented by a 4-index tensor, because this every number in this 4-index tensor, it's going to multiply a product of 4 creation and annihilation operators. So in general, there is n to the 4 of these numbers. Okay, so n to the 4 elements, n to the 4 two-body integrals. Because so n to the 4, it's the number of generic interaction terms that we have in our fermionic Hamiltonian, and being the number of fermionic modes in our system. And finally, remember that we are doing our calculation in the Born-Oppenheimer approximation. And in this approximation, the position of the nuclei, it's fixed. So the nuclei don't move, and their contribution to the molecular energy is really like a static, classical Coulomb electrostatic repulsion. And to get the value of that repulsion, let's define a nuclear repulsion energy by getting it from our molecule object. And let's print it to check its value. Okay, so this number is expressed in artery units, and it tells us the repulsion between the lithium and hydrogen nuclei in our molecule. Okay, so now that we have fully specified everything about our molecule, let's start by making the first step towards the construction of a qubit Hamiltonian. Now, the first step is in Qiskit is the creation of a fermionic operator. So to do that, let me first mark this cell as the start of a new paragraph, which I'm gonna call create a fermionic operator, just because of a lack of fantasy. Okay, and so in this new section here, first of all, let's import from Qiskit chemistry a fermionic operator class, and with this class, let's create an instance of a fermionic operator, and let's call this for op. A fermionic operator object is created by feeding it a 1 and 2 body tensors that contain the 1 and 2 body integrals that specify our molecule. Okay, so in this case, H1 and H2. And also let me define some variables that are going to be useful later. So the number of spin orbitals in our system, which is related to the number of orbitals in our molecule multiplied by a factor of 2 because of the spin degeneracy that we have in this system. And then the number of particles, which is basically the number of electrons that we have in our molecule, which is going to be a sum of a number of particles in the alpha and the beta sector for our molecule separately. So let's sum up these two fields. Let's see if all of this has worked. Yes. Okay, also, if you remember, I told you in the class that sometimes we can freeze certain fermionic modes and we can remove them out of our model if the physics of our model allows us to do so. And so in this case, I'd like to freeze the inner 1s orbitals for the lithium atom, because look at this one-body integral matrix. So what you see is that the value for the inner 1s orbitals for the lithium, this is actually 1s orbital for the lithium. So the ordering that Qiskit is using in this case is first list all the lithium orbitals, just because we wrote the lithium first. And then the order is, this is the 1s, this is 2s, and these are the 3p orbitals of the lithium. So this would be px, py, pz, and then it will be, we will have here the 1s orbital for the hydrogen atom. Of course, these are atomic orbitals, so what happens in reality is that the driver runs a Hartree-Fock, a molecular calculation. So these orbitals are actually hybridized, so hybridized versions of the atomic orbitals. But still, this low energy 1s inner orbital for the lithium doesn't hybridize much. And you can see that its energy is actually much lower than the energies of the other orbitals. So this means that with very high chances, two electrons with spin up and spin down are going to sit in this 1s molecular orbital. So we can, and not interact with the other fermionic modes in the system. So we can assume that two electrons are there and they're going to be freeze and they're not going to interact much with the rest of the system. So, and the index of these two orbitals is of course 0 and 6, okay? Because we have a alpha and beta 1s orbitals. So the total number of orbitals is 12, okay? So we have all 6 orbitals with type 6 alpha type orbitals and 6 beta type orbitals. So we have a 1s orbital in the alpha spin configuration at position 0, and another one in the beta configuration at position 6. So all of this is to say that my freeze list is going to be composed by 0 and 6. Also, I like to remove some orbitals. So remember, we can remove orbitals whenever we think that they have very high energy and they do not interact much with the other orbitals in the systems, and we don't have a high enough number of particles to populate those high energy orbitals. So in this case, I think for the sake of this lab, I'm going to remove the pz orbital from the lithium molecule. And so the pz orbital is in the 0, 1, 2, 3, 4, in the fourth position here. And then there's going to be another pz orbital with the opposite spin configuration, which is going to lie on the 10th index. But now we have to be careful, because if you want to do first a freezing operation and then a removal of orbital operation, the actual indices that we want to remove, they have to be scaled by the orbitals that we freeze first. Okay, so we should put here orbitals number 4 and 10, but actually what comes down to is that we're going to remove orbitals 3 and 8. Okay, this is because 4 and 10 are going to be rescaled by the absence of these two orbitals, which are in the freeze list. Oh, sorry, let me call this freeze list. Okay, so I have defined my fermionic operator. I have a freeze list and a remove list. So let's start freezing and removing orbitals. The way we do that is, let's define a frozen fermionic operator and in this way, together with an energy shift, which is going to come from the fact that we are offsetting the energy of our system by implying that the two 1s electrons of inner 1s electrons on the lithium atom are going to be frozen. So they're going to contribute, not interact with the other electrons. So they're going to contribute effectively to the energy of our molecule just by a constant shift. And so both this frozen fermionic operator and this energy shift are computed by the freezing method in the fermionic operator class. So let's call that fermionic mode freezing, and let's feed to this method our freeze list. And now we have to be careful, because we have to rescale the number of spin orbitals and the number of particles by taking into account the fact that we have frozen 2 electrons. So the number of available spin orbitals, sorry, just caps. So the number of spin orbitals, it's going to be shifted by how many orbitals are in this freeze list. Same with the number of particles. Okay, remember that we are assuming, we are basically removing 2 electrons out of the system and assuming that they are there in their inner 1s orbital and not contributing to the this electronic structure that we're trying to calculate. Okay, now we have defined our frozen fermionic operator. Now let's print the one body. This is the one body matrix that refers to our frozen fermionic operator. Now note that, of course, the number of fermionic modes in this one body operator, it's reduced by 2, right? So it's, instead of the 12 original mode, the 6 in the alpha, 6 in the beta sectors, we now have 1, 2, 3, 4, 5 modes in the alpha sector and 1, 2, 3, 4, 5 modes in the beta sector. So as we expected, by freezing two of the fermionic orbitals, we have a fermionic operator which has 2 less mode inside of it. Okay, after freezing, let's remove the 2 fermionic orbitals which we deemed too highly energetic to contribute anything to this dynamic, highly energetic and not very interacting. So to remove them, let's use another method of the fermionic operator class, which is called fermion mode elimination. This is what I'm trying to call here, and let's feed this method with the remove list. And again, now we only have to update number of spin orbitals, right? Because we are not storing any electrons to these orbitals that we want to remove. So the only thing that's going to be updated is the number of spin orbitals. And again, let's print the fermionic operator, frozen and removed, I guess. Okay, what up? Oh, excuse me. This should be F. So the net result of this operation is a fermionic operator which has now only eight fermionic modes. So it's 1, 2, 3, 4 in the spin alpha sector, and 1, 2, 3, 4 in the spin beta sector. Okay, so now we've recalled that we've started from a fermionic operator which had 12 fermionic mode in it, and we nailed it down to a fermionic operator with just 8 modes. Okay. All right. So now that we got this trim fermionic operator, let's move on and let's try to map this fermionic operator to a bunch of qubits. Let's map it to a qubit operator. So before doing that, let me define a new section, which I'm going to call create a qubit operator. Just maintaining my section labeling style. Okay, now remember from the class, so the first thing I told you about fermion to qubit mappings is that there is more than just one mapping. So in this case, let's set up the parity mapping for reasons that you're going to see in a few notebook cells. And let's finally define our qubit operator by using the mapping method of the fermionic operator class in this way. And let's print the qubit operator. As well with, let's print its details. Again, now we're going to see what are the details of a qubit operator. Wait a few seconds. All right, so this is the outcome. So by printing a qubit operator, what we get is a summary of this qubit operator. So what we know so far is that this operator is stored in the memory as with the Pauli representation. So it means that it is stored as a sequence of Pauli operators and coefficients. Okay, as opposed to a matrix representation of the same operator, which would have been exponential in the size of our system. And then the number of qubits on which this qubit operator is defined on, which is 8, which is coherent with the number of fermions that we were getting at the end of our freezing and elimination mode removal procedure. And also we know the size of this operator. So the size of the operator expressed in the Pauli's representation is the number of Pauli operators that compose a given qubit operator. So in this case, it's 193 Paulis. And by printing the details of this qubit operator, you can really see each one of these 193 Paulis here, Pauli operators with its corresponding coefficient. Okay, so now finally we have a qubit operator. So notice that we can also change the mapping here, and we would get a different operators, always defined on 8 qubits, and also with the same number of Pauli operators. It's just different because the mapping is different. Okay, let's get back to our parity mapping. Okay, we got back to our qubit operator defined on n qubits with parity mapping. Okay, another thing that we've gone through the class is what happens if this operator has certain symmetries, right? So what we can actually do is exploit these symmetries to take off qubits out of the representation of this operator. And this is going to be useful if we want to compute, for example, ground state properties of this operator here, this molecular operator here. So first of all, let's check if the qubit operator defined so far has symmetries. And so to do that, we're going to import the Z2 symmetries module from Qiskit Aqua. Okay, so to do that, let's import Qiskit Aqua operators. Let's import Z2 symmetries. And let's actually run the find Z2 symmetries method. So this method here, it's this function here, it's gonna take in a qubit operator and spit out a bunch of symmetries, which eventually are gonna be present in the target qubit operator. So let's print them. Let's see what happens. Okay, this is the outcome. So we actually have found that our qubit operator has 3 symmetries. But let's have a closer look at these symmetries. Specifically the first and the third one. Okay, so what you see is that there's just one Z in the middle qubit here, and there's one Z in the final qubit here. Okay, so note that this is not the first qubit, this is the final qubit. This is how the Qiskit convention works. Okay, so the actual the highest significant digit is the one on the left, if you want. So middle and final qubit, we have a Z type of symmetry. What is this? Okay, so what this is telling us is that the parity of the total number of particles is conserved. So remember the meaning of the parity mapping. So the parity mapping has encodes for the qubit at position I, the parity of all the fermionic modes of index I or less than that. So the parity of the qubit, of the last qubit, it's going to actually encode the parity of the number of particles that are present in our system, basically the number of particles that are in every fermionic mode. Okay, so this symmetry here, it's nothing else than the parity of the total number of particles in our system, because we have used the parity mapping. Then I guess now you could guess what is this Z symmetry in the middle here. This single qubit symmetry is nothing else but the parity of the alpha type particles. Okay, so these two symmetries together are telling us that spin and charge symmetries are conserved in our system. And this is something that these two symmetries are always going to be there if we target non-relativistic molecular chemistry. Okay, now, since these two symmetries are always going to be there, we actually have devised a special function in Qiskit just to get rid of these two symmetries. So let's use this function and let's see how this function gets rid of these two symmetries, which in terms of encoding our qubit operator, it means that we will be able to encode our qubit operator with 6 qubits. So with the number of qubits, which is diminished by the number of Z2 symmetries that we are targeting. Okay, so let's define a qubit operator, a tapered qubit operator with this label T. And let's get this tapered operator by calling a 2-qubit reduction function, which is in the Z2 symmetries class. And let's feed to this function our qubit operator and the number of particles. Remember, now the number of particles is 2 because we have frozen 2 electrons at this step here, and we have also updated the number of particles. So number of particles is 2, and so this function is able to infer which sector for these two symmetries to choose just based on the number of particles that we have in our system. Okay. And after this, let's print the tapered qubit operator together with its details. Let's see what we get. Oh, we got an error. So it was actually print details. Okay, so now we see that our tapered operator, it's actually defined only on 6 qubits instead of the previous number of qubits, which was 8. So we have removed 2 qubits. And now that we have got our 6 qubit operator by removing the 2 spin charge symmetries that every non-relativistic molecular Hamiltonian has with the 2 qubit reduction function, let's actually double check that indeed the ground state energy for our tapered qubit operator is the right ground state energy, right? So to do that, let's import from Qiskit an exact NumPy eigensolver. So this eigensolver is going to find us exactly the ground state of our qubit operator, our tapered qubit operator. Of course, this procedure has an exponential cost, but we're just gonna do this just to check that our qubit operator has indeed the right energy. We don't actually need this operation in running any of the quantum algorithms that we are interested in. Okay, so this is just a check. So we have, let's import the NumPy eigensolver, and then let's use it this way. Okay, let's get the result, and let's get this this field of the dictionary here, which is going to be our ground state energy, and let's print it. But let's not forget that the ground state energy for our qubit operator has to be shifted by the nuclear repulsion energy that we computed previously, and also the energy shift coming from the freezing of the two 1s orbital for the lithium atom. Okay, so these the sum of these three energies gives us minus 7.88 arteries, which if you take a look at this this plot here, it kind of matches this. Kind of matches the value, the energy value at the interatomic distance of 1.6. So, you know, this 6 qubit operator is capturing the physics of the molecular system that we're trying to tackle. Okay, so this concludes the first part of this lab session. In the second part of this lab session, we're gonna play a bit with the variational ansatz. We're gonna see what kind of circuits are needed to produce the variational ansatz, how to get those from Qiskit, and also I'm gonna talk about reference states. Right? So let's actually, let's call this section, let's give a title to this section. And let me call it variational ansatz, or let's say creating variational ansatz. It makes sense actually to start talking about the reference state before diving into our how variational wave function, variational ansatzes are created. You know, computation of ground state properties have to start, quantum computation of ground state properties have to start from a good reference state. A good reference state for molecular systems close to the bond distance, it's usually the Hartree-Fock state. So in Qiskit, we have a Hartree-Fock class, which you can import, and to check what is the Hartree-Fock state in terms of qubit representation for a specific molecule that we're targeting, and also what is the quantum circuit that is needed to prepare that Hartree-Fock state. Okay, so let's check that out. Let's import the Hartree-Fock class from Qiskit. So we have to go into components, initial states, and we have to import the Hartree-Fock class, and let me initialize an instance of the Hartree-Fock class. And so to go through this section, we're just going to pick a very simple, you know, toy model just to see what are the features of these reference states and variational ansatz. So we just let me set the number of orbitals in our system to 4, and number of particles to 2. Okay, so this is nothing to do with the previous lithium hydride molecule. This is just a some toy example to play with. And let's actually use as a qubit mapping the Jordan-Wigner transformation. But the reason we use the Jordan-Wigner transformation is because with the Jordan-Wigner mapping, it's easier to have an intuitive understanding of what are the you know, occupational, what are the fermionic modes that are occupied and empty, and also there's more of a feeling for how to initialize our quantum hardware into the reference state. Let's see that in a second. So first of all, let's print the bit string corresponding to this initial state. A bit string is nothing else than a list of occupation numbers for the fermionic modes that we have in our system. So this bit string is going to be 0 and 1, respectively, if the mode that it's listed, it's empty or occupied. Actually, the bit string is encoded as a Boolean, as a list of Boolean variables. Yeah, so let's see that in a moment. Yes, so this bit string in our case has 2 particles. So the Hartree-Fock state has 2 particles inside of it, distributed on 4 modes. So the bit string looks like this. So we have 2 true, which means that the particle is here and a particle is here. So these are 4 fermionic slots, 4 fermionic modes, and only 2 of them are occupied. But now if we wanted to create a circuit that initialize our quantum computer in this Hartree-Fock state in the Jordan-Wigner representation, what we would have to do is, let me define now a toy Hartree-Fock circuit, which refers to this initial state here. Actually, let me just call this Hartree-Fock circuit. Let me drop the toy label. So let's call this method construct circuit, and let's plot it. There's one typo here. Okay, so this is actually the quantum circuit that prepares our toy Hartree-Fock state. Okay, so it acts as the identity on these 2 qubits, which represent the occupation of the fermionic modes, which are actually empty, and it just flips qubit 0 and 2 from 0 to 1 because these 2 guys were occupied. Okay, that's it, simple. So now that we have started from a good reference state, let's see how to build a variational ansatz. So the variational ansatz that we want to consider in this lab session is a unitary coupled cluster ansatz with single and double excitations. Okay, so we start by importing the unitary coupled cluster ansatz, or UCCSD. So it's going to be components and variational forms, and we have to import UCCSD class. And let's define a UCCSD variational form by initializing it with a bunch of parameters. Okay, so let's matching the Hartree-Fock parameters. Let's pick a number of orbitals to be 4. Let's call this variational form. 4 orbitals, 2 particles, Jordan-Wigner mapping, excitation type. So what is excitation type? So excitation type is an option that allows you to restrict yourself to just one body, so single excitations. So this means that we can only remove an electron in a orbital, in a occupied orbital, and create an electron in an empty orbital, and that's it. And a double type of excitation will be an excitation in which we remove two electrons from two occupied orbitals and we create them in two empty orbitals. So for the sake of this lab, let's restrict ourselves to just a single excitation type here for simplicity. And also let's restrict our excitations to the beta sectors. So we're not gonna consider excitations on both alpha and beta, but just limit ourselves to just one spin sector. And let's feed to this operational form the Hartree-Fock initial state, which we have defined before. Let's just set two qubit reduction parameter to false. You got to do that. I think the default is set to true, and also the parameter reps, which I'm going to explain in a moment. Okay, so after we have set everything about our UCCSD version form, we can now check how many excitations and how many parameters has this this wave function that we are creating. So to do that, let me use the field single excitations and number of parameters. So if there's no typos here, this should work. Let's see, there is a typo. Okay, yeah, there was a typo here. So it was UCCSD. And now it should work. Yes, okay, so what we have obtained here, it's a list of single excitations for this unitary coupled cluster variational form that we have defined. And note that the list of single excitations is correct. So it's an excitation which is going to remove an electron from orbital number 2 or qubit number 2 if you want, and it's going to move it onto the empty orbital number 3, so the last one. And this is consistent with the fact that I only picked beta, I only picked excitations in the beta sectors, and I only picked single mode excitations. Okay. So we only have one parameter. So in this case, it will be like a very trivial VQE, only one variational parameter, and only one excitations. But this is for the sake of simplicity in this tutorial. All right, now let's have a look at the actual circuit that implements this variational form. So let me define a variational circuit by using this construct circuit method. So construct circuit is going to take as an input a value for the parameters in the variational form that we are considering. Since we only have one parameter, we only need one value. So I'm going to feed the method construct circuit with just one number, which is the value of the variational parameter I'm considering here. And then finally, I want to plot this var circuit to have a look at it. There you go. Okay, so you see that in this circuit, we have, first of all, the two gates that were defining our our reference state preparation here. So the preparation of the Hartree-Fock, this toy Hartree-Fock state. And then you see the actual circuit for the the implementation of this hopping, fermionic hopping term from fermionic orbital 2 to fermionic orbital 3, which in the Jordan-Wigner representation, it's just a hopping basically from qubit 2 to qubit 3. So you see that actually these this scheme, these two control knots for each of the two separate terms that represent this this hopping here, as I told you in the class, are here. So this is one Pauli that this is one component of the hopping term, one Pauli, and this is the other one. And note that there was a field in the this variational form which is called reps. So if we actually increase this to 2, what we get is basically we get a repetition of the number of excitations that we are considering. So in this case, since we are considering just one excitation, we will have the same variational excitation repeated twice. So to actually print this, I have to feed it now two separate parameters, right? So one for the first time that I'm trying to vary this hopping from qubit 2 to qubit 3, and another parameter for the second time. Okay, so basically what we get is a repetition of the initial variational circuit by a factor 2. Okay, so we get the same circuit repeated twice. And in general, if we had n excitations, we can think of repeating them n times. This is kind of a relaxation of the implementation of a trattorization for the UCCSD variational form, as we have seen in the class. Okay, so this concludes the last part about variational forms and preparation of variational forms and reference states. I'd like to leave you with a little bit of a homework. So let me define a homework section here. And I'm going to call this homework the last symmetry standing. So, and I guess the careful listener would have noticed by now that what I mean by last symmetry standing. In fact, when I show you the symmetries for our original 8-qubit operator, we have seen that there were actually 3 symmetries present, and then we have just eliminated 2 of those. Okay, so we have just eliminated the symmetries which were related to the spin charge symmetries in our system. So there is actually a last symmetry standing, surviving, and I want you to try to taper this last symmetry. Okay, so to double check that, let's see that that symmetry is still there. and has survived the tapering of the two spin charge symmetries. So let's call again the find Z2 symmetries method for in the Z2 symmetries class, but this time let's apply it to the tapered qubit operator. And let's print the symmetries that this method will find. And as predicted, we have one symmetry which is still here. Okay, so what I will like you to do as a homework is trying to use Qiskit to take now this tapered qubit operator and bring it down from its current 6 qubits to 5 qubits by removing this, this last symmetry, which is still standing. Okay, so with this homework assignment, this lab session concludes here. I'd like to thank you for your attention, and please enjoy, have fun, and enjoy the rest of the Qiskit Summer School.